Xi from TigerGraph. So this is about a benchmark we are using LDBC SNB dataset and workload. So this is derived work from LDBC, and this presentation does not represent official LDBC benchmark results. And our work is mainly relied on the LDBC SNB BI benchmark dataset and queries. And the work is a benchmark, but it's a derived work benchmark, and it's not audited. So we emphasize these numbers do not constitute official LDBC benchmark run. And the purpose is to share our experience and insights from conducting a large-scale stress testing on TigerGraph's distributed graph engine. So first, I give some background on the LDBC BIWorkload, and it consists 20 read queries. They are complex graph patterns and touching a significant portion of the graph elements. And also the LDBC SNBBM benchmark is designed based on choking the query engine based on graph patterns. It includes explosive and redundant multi-joins, and also have expressive path findings. And during the benchmark run, it has macro batches to simulate daily fresh data update of the database state, and it consists a set of insert and delete operations, and the batch data represents a given time period. For example, 1 day is one batch. And we set up the benchmark environments using 72 AWS cloud machines. And the model is R6A 48X large. And each machine is using Amazon Linux AMI kernel 5.10 operating system. And CPU is AMD EPYC at 3.5 gigahertz, and each machine has 192 core, and also 1.5 terabytes memory, and the rest is the standard configuration for this particular AWS machine. And we use the TigerGraph 3.7. This is conducted a long time back. Now TigerGraph is on 3.11. And we also use LDBC specification 2.2 and the data generator 0.5, and the driver implementation is 1.0.2. So the initial modification to the LDBC benchmark is we use the data generator, and we can successfully generate 30 terabytes from the official data generator. And in order to make 100 terabyte data set, and we did a modification for the schema first. If you look at the LDBC schema, it has two subsets of graph elements. And the first is the dynamic part, which usually the volume increases as timestamp elapses. And the second subset is static vertex and edge types. Those vertices and edges represents static units or objects, such as company, university. You don't tie those entity with the time dimension. So what we did is we don't touch the static schema part, but we triple triple the dynamic attributes part, vertex and edge part. For example, the comments, we create 3 comments using the same schema, and comment become comment 1, comment 2, and comment 3. And for the person vertex type, we created 3 index the vertex type person 1 to person 3, and etc. We did the same for post and the forum, and also for the edge containers. For the edge container, we didn't do anything. We actually just duplicate the vertex type of the dynamic vertex part. So with this schema change, in essence, we actually duplicate the dynamic vertex types, and we modify the benchmark query to activate corresponding duplicate vertex type. So if if a query starts with comment, and instead of activating 1 comment, now we need to activate 3 comment vertex types. And for point query, we actually don't change anything, and I will give detailed example later. So for example, here, if benchmark query in the LDB CBM benchmark starts from all the posts, instead of starting from post 1, which is the original clone of the dataset, we start from all of the 3 duplicate post containers. So post 1, post 2, post 3. The 3x datasets got activated from this query. And if a query starts with 1 dynamic vertex, for example, person 1 has a person ID, and we don't change anything. We just start from that particular person ID, but use 1 container person 1, one vertex type person 1 to continue the benchmark query. And if a query starts with a static vertex, and we use that static vertex to follow the traverse pattern, and if it touches dynamic vertex type, we include all the dynamic vertex type in the original 1 vertex type to bump the reach of this query. And this is the DDL to set up the modified benchmark schema. So this is one example. So in the original schema, we have 1 vertex type, dynamic vertex type comment. And in the new schema, we created 3 comments container and indexed by 1, 2, 3. We did the similar thing for other dynamic vertex type, such as posts and other forum, etc. And in order to adapt to this bootstrap dataset, we also need to modify the DDL of the edge container. And since the edge container will connecting the dynamic vertex type and other vertex type. So here we show one modification. We don't change the edge container, edge type container name, and we just modify our DDL to allow the dynamic vertex type form 1 to form 3, Cartesian product to post 1 to post 3. Similarly, if original the edge connecting comments to comments and posts, now we just list all of them in the starting source, and then list all the duplicate one in the targeting to vertex type list. And we do this for all the edge connectors. So this is the final dataset cardinality. And the vertex end up having 217 billion vertices, and the edge cardinality reaches 1.6 trillions. And we put this in the GitHub for people to reproduce our benchmark results. The benchmark workflow and run is following actually the LDBC VRDB 2023 paper, and we follow exactly the same approach. First, you do a power batch run, which interleaving the write and the read, but sequentially run those queries. And then after the power test, we run a throughput test. And in this particular case, we don't run throughput batch concurrently. We still sequentially run them. And this benchmark runs the power and the throughput tests of the 20 query variants with 5 substitution parameters. In total, there are 140 queries. And for this 1 trillion edges, the loading time on the 72 machine is 12 hours and 45 minutes. And per machine, we observe 17 gigabytes topology after loading. And if you aggregate this from the 72 machine, it ends up 44 terabytes. And the original raw data is 108 terabytes. So the compression ratio is about 41%. And the loading speed is about 117.6 gig per hour per machine. And we use the power formula and throughput formula at scale factor and report the corresponding results here. And if we break down the read time and write time of the 5 runs per query, and we can see that total read time of this 140 queries is about 5 hours. And the total write time, including the batch update, is 4 hours. And in order to speed up the query, we have the pre-computation for certain queries, and we report the time here. So this is the 20 query variation, including their variations, and each query's min-max time and the average time of their 5 run, and each run uses different parameters generated by the benchmark. So most of the query actually finish within 1 minute. Some long-running queries taking 270 seconds. So in conclusion, TigerGraph actually can handle the complex LDBC BI OLAP queries at a scale of 1.6 trillion edges and raw size 108 terabytes on 72 machines. And 11 of the data-intensive queries returned results within 1 minute, and the rest took 1 to 2 minutes, depending on the different query. And to our knowledge, no other graph or relation database has demonstrated similar performance at such scale. Yeah, that's conclude my talk.
Any questions? I will take a look at online participants. Okay, sorry.
Thank you. Yeah, Thank you, Mingxi. So this this is the BI workload, I suppose, and so so you chose to run the throughput run, but single batch at a time.
Yes.
But what did you say about the query parameters? You only used 5 query parameters.
Yeah.
Normally there are many more query parameters, aren't there?
Yeah. Usually you have 30 query parameters per query.
Yeah.
And
Yeah.
we only run 5 because during the length of the time took longer. So we want to control the total run within 1 day.
Okay.
So we could run 30, but at that point, the engineer just estimate the time to be 1 day. And since we run the AWS machine, we don't want to go 6 days.
Okay. So by the way, and the whole exercise of kind of this kind of triplication of the data, it is well, it is not of an official way of doing this, I suppose.
No.
This is big. Why is this?
So this
Is this a limitation because of a limitation of the data generator?
Yeah, at the point we tried, this is about 1 year ago. The data generator can only support up to scale factor 30K.
Okay, is that still the case?
Still the case.
Okay.
Yeah.
And is it difficult to fix that? Because otherwise, I mean, the exercise could have been to just fix that. And
yeah, I think I talked to Gaber, and he think need another funding to support.
Okay.
Support one person half year or 1 year to fix it. Yeah.
Yeah. Okay. Well, at some point it probably needs to be fixed.
Yeah.
Okay. I do note. I mean, it is an attempt, but normally the kind of the connectivity of the graph is also a function of the size. So it gets denser, I think, with higher scale factor. So it's not exactly. So the amount of edges would actually have been at least a bit different if it were following the data generator normally.
Yeah, I think the density definitely will be more realistic with the data generator, and we think this is maybe more complex than the data generator.
I see.
More stressful, yeah.
Yeah. Okay. Okay, thanks.
Yeah.
Yeah, it's that kind of discussion you just had, which is why we are so insistent that we don't report results unless they're fully complete, audited, using the standard and all the rest of it. And so thank you for the disclaimer at the front of this presentation, which is exactly, I could just use this as an opportunity to explain to everybody. Fair use policy says if it's derived, if it's modified, if it's not complete for any reason whatsoever, you have to explain how and why that's true, and you have to have this kind of statement. It's not an LDDC benchmark result. So this is absolutely exemplary. Thank you very much for doing that.
Yeah.